Well, good afternoon. Take your seats. So I'm really happy to be here and see you here. It's my first time at DevBcn, and today I'm going to present you a healthy diet for your Java application. Before we start, let me introduce myself. My name is Marharyta. I work as software engineer at Sonar. You probably heard of this company. And I do sometimes speaking at conferences, and in my previous life, I was organizing some conferences in my native city. I'm also a big fan of different JVM languages like Java, Kotlin, Scala, and for my everyday job, I'm writing static code analyzers for them. And this is my Twitter handle, and you can follow me if you want. There is another important thing you should know about me. I am Ukrainian. I was born and raised in Kyiv, and currently we have big problems with our neighbors. And if you feel like you want to support us to fight for our freedom, you can scan this QR code and do some donation to this charity fund. The most important part of my presentation is over, so now we can relax, and let's continue. A short disclaimer. The things that I am going to tell you today, they are not a rocket science. You probably already knew them or heard about them, or as my husband told me when I presented it to him, you might not be impressed. However, I'll try to give you some structurized knowledge, and you'll learn some algorithms that can help you in how to deal with your memory leaks. And of course, there is no silver bullet, because every single problem with memory is unique, and you have to find your own solution. However, I will try to provide you some algorithms and some hints. So, how it all started? Why am I here talking about memory leaks and so on? You probably know this guy, or you might not know this guy, but this is Alexey Shepelov, a principal engineer at Amazon. And he's famous for his valuable contributions in OpenJDK and some projects like GMH, JC Stress, Java Object Layout. And in our company, he is famous for analyzing OpenJDK in Sonar Cloud. So you can see the quality gate is a little bit failed, but you can see that they're fixing some bugs, vulnerabilities, code smells. So technically, Sonar is helping to make JDK better. So that's nice. And one day, he came to us with strange request. Like, I want to analyze Java and C++ code of OpenJDK in Sonar Cloud, which is great, using 3 GB of RAM. And he cannot. And now, we need to reflect a little bit why this is actually a valid request to us. If you ever used SonarQube or Sonar Cloud, you can raise your hands. By the way, if you use SonarQube or Sonar Cloud, oh, a lot of people using it. That's great. You probably know that usually our analyzers are part of your CI jobs. So technically, you are not just paying to Sonar for the analysis and for all the cool features, but you're also paying to AWS or Azure or Google Cloud or any other cloud provider to host this analysis. And it means the more memory are eaten by our analyzers, the more you pay for this. And the same comes for SonarLint, which is our IDE extension, because it's run in the IDE, and we are using resources of your local machines. So technically, you pay for the analysis. And that's why it's extremely important for us to keep this in mind and to take care of how much memory we are using, because it's you who are paying for this memory, and we care about our customers. And at the same time, I just came back from my maternity leave, and I was trying to get back into shape, lose some weight, trying to have some healthy habits. And all these two topics messed up in my head, and I found a lot of analogies between losing weight and getting back in shape and fixing memory problems in our analyzers. And that's how the idea of this talk appeared. So, at some moment in time, I asked myself that maybe I'm making applications fit too, and I found out that there is some common algorithm. So yeah, first of all, when I wanted to get back in shape, to lose some weight, I asked myself, is there any problem? Because if I look into the mirror and I like what I see, why should I care? And that's extremely important. Don't listen to anybody. If you like what you see, you don't have a problem. We don't all have to be top models. Everybody is unique and nice. Only if you want to change, only if you don't like what you see, you can identify that there is some problem and work on this. The same comes for your application. If you're satisfied about how much memory is consumed, why should you care? Why should you invest your time, money, resources into researching something that you're already satisfied with? So this is the first and very important question that you need to ask yourself. Is there any problem? But how should I know, is there any problem or no? I have doubts, I don't understand. And as a Java developer, I don't want to actually think about memory, because that was exactly the reason why I stopped using C++ and switched for Java, because we have garbage collection. Why should I care? The problem is, garbage collector is not a wizard. He's a cool guy that can help you. However, he cannot collect the trash or objects that are still referenced. And this is our job, to make sure that we don't reference the things that we don't use. So, in order to understand if we have problem or no, there are some symptoms. So, if we're talking about body, it could be like your clothes are too small, you have to buy bigger, your fat percentage is too high, you want something lower. It's maybe difficult to run, walk, do some physical activities. Your BMI is too high. You might be always hungry, and you're not satisfied with your appearance. These are the symptoms of some problems in your body. In your application, there are also some symptoms. For example, out-of-memory error. If you see this, it doesn't tell you definitely that you have memory problem, but it signals you that maybe there is something to investigate. You're giving more memory to your application, but this doesn't help. Whatever you give your application, it's always eaten. That's another symptom. You spent much time on garbage collection, and you might know that GC poses, they can drastically influence your performance. And for example, you're also spending not just too much time, but you're spending too much CPU, because you have some memory leak. Garbage collector tries to collect the trash, but he failed, and he spends a lot of time and CPU on this. And so on. There are a lot of other mild, not mild symptoms, but they all together can signal you that there is some problem. You need to investigate this. Okay, we learned how to identify whether there is any problem or no. Another point is how big is the problem? And we cannot know how big is the problem until we measure. So the next step would be to measure. When we're talking about body, usually it's weight, fat muscles, BMI, heart rate. You can do some blood tests. You can record your eating habits, so on. And for application, you can track your memory usage, time, CPU usage. You can generate heap dumps to actually see what's inside the heap. You can look into logs, and so on. As much as possible, you should collect the metrics as much as possible, so you can have the full picture of the problem. Because it's extremely important to understand that just memory usage is not enough. For example, you see this graph, and raise your hands if you think that there is a leak. And raise your hand if you think there is no leak. Okay, so the honest answer would be, I have no idea. Like, how could you know if there is a leak or no? Just looking at the memory, because it could be just natural consumption. Another graph that can help you, for example, tracking GC activity. This graph shows you that garbage collector tried to work, tried to do something, but he failed, so these two graphs together can signal about the problem. But just the second one is not enough, so never look at a single picture, try to gather as much as possible. Okay, Alexei Shepelov knows how hard it is to investigate memory leaks, to gather all possible metrics. So he, of course, helped us. He generated heap dumps, he provided logs, memory analysis, and everything that could help us in our investigation. And the first thing that we looked at was the stack trace out of memory. We looked at this attentively, and then we realized that there is this package, com.sonar.cpp.something. And we stopped for a while and like, okay, .cpp means that it happened in a C++ analyzer, and we are in Java team. Why should we care? We are like not these people. Let's just take this request, send it to C++ team, and say, we are done, it's their problem. And now, I would like to ask you to be very attentive, because I need to reveal you one secret. It's an extremely important secret that will change your life forever. So if you don't want to hear it, close your ears. So are you ready? If you have out-of-memory error, you have a stack trace for it. The best thing you can do with this is to take it carefully, very, very carefully, and throw it away. Because out-of-memory error is like the last drop in your cup. It happens when you ran out of memory, but it doesn't show you where was the real problem. And in our case, the problem was actually in Java Analyzer, but out-of-memory happened in C++ Analyzer. But we cannot just give it to that team, because we need to investigate more. And next time, when you experience out-of-memory in the products, like in our products, Sonar Cube, Sonar Cloud, Sonar Lint, or any other, don't send us stack traces. Send us heap dumps. So we learned what to measure. We have all these measurements. What would be the next step? The next obvious step is to analyze it. And I think the best way to show you how to analyze it is to actually show you some demo. Oh, let me get back to my laptop, and I will show you some visual view. Raise your hands if you are familiar with this tool. Oh, a lot of people. But I think still half of you have never seen it. So I encourage you to just use it for a while and have a look there, because it's a really important tool for every Java developer. So it shows you some metrics, some numbers about your heap. So which objects you have in your heap, how much memory it consumes, so on. A lot of lines, a lot of words, a lot of numbers, extremely hard to investigate. As for me, I have just like one first step is to look attentively on this and try to find something that catches my attention, something that is like unusual. For example, here you can see there is 97.3% of memory accumulated in instances of byte array, which is strange. It's like not usual for every application. So let's have a look more attentively there. So here you can see the instances of byte array and how much memory they take. Here you can learn how many of them we have. And one of the most important things you can learn through like Visual VM and in heap dumps is to investigate garbage collection routes. So technically, it's why this object is still in a heap, who references it. And here you can see that this byte array is value in some full name, which is like some of the value in your array list, come on, and it all is referenced through some static field names cache. So when I saw that it's static, something like triggered in my brain, and now I have a question to you. So, guys, please raise your hand if you think that static fields are eligible for garbage collection when the last instance is collected. OK, so nobody thinks so. And who thinks that when class instance is collected? I think so. I thought this initially. So when JVM exits, I just feel you had a really great lunch, so you don't want to raise your hands, yeah? But I need your help here to investigate. So now, when class is unloaded, anybody? Great. And none of the above. Cool. So the most honest answer that people who said P and D are half right, half not right, and let me explain you why. When we are working with our application, we usually deal with some instances. So you create some object with new, and this is an instance. Every instance holds a reference to the class. Yes, which is like, OK, obvious. And every class holds references to its static fields. And one more important thing, every class also knows about the class loader that loaded this class. And every class loader knows about all the classes that it loaded. So if we want to make static fields eligible for garbage collection, we need to make sure it's not referenced. So there should be no class, and it means there should be no instance, and there should be no class loader. And the next question is, when is class loader garbage collected? And in most cases, sort of never. It lives as long as your application lives, unless it's your custom class loader. So the correct answer would be that static fields are eligible for garbage collector when there is no class and there is no class loader. And by default, it's never. So static is like sugar. It's extremely easy to make something static. It's extremely easy to use it, but the consequences could be huge. Like static members live almost forever. Static members should be avoided. Static members, if you cannot avoid using them, please don't make them mutable. Don't use lists or maps or any collection that can increase the amount of memory. And even if it's mutable, if it's a list, please make sure they're not updated from non-static methods. And in Sonar, to help you avoid some common mistakes, we have rules. One rule is that mutable fields should be public static, and another rule is that instance methods should not write to static fields. However, it's not like all possible problems with static, just a tiny subset of it, but still better than nothing. So be attentive when Sonar signals you with these issues, because they can lead to memory leaks. Okay, we learned a little bit how to analyze the measurements that we have, but sometimes it's a little bit harder to just look at this and see static. Sometimes you need more steps to find the root cause. So let's look at a little bit more complex demo. So again, Visual VM. Again, we can try to search something catching our attention, and it's again byte array. So there are some elements here, and you can see that it's again referenced through some names cache. It sounds fishy because things that are used for caching are, like at least in Sonar, are big candidates for memory leaks. And if we look at a few more instances, we can see that this pattern repeats, that they are all referenced through names cache. And now it's time to look a little bit in the code. So let's get here. This is example controller, so the class that was referenced. This is the names cache. It's not a static field, so let's investigate a little bit more. It's updated through hello method, which is just a method in a controller. And if we look attentively here, we can see that variable name can either be A or B. Do you agree? So let's put some comment, A or B. Okay. The next step, we create a full name out of this string. So technically, it could only be f of A or f of B. Fair? Fair. And then we put this into a map, and full name is a key. So technically, in a map, we can only have two elements. Yes? So it could only be FA and some counter, or FB and some counter. But for some reason, we saw that there are a little bit more than two, like around 10,000. And do you have any idea where the problem could be? And yes, like if you just look at this code, it's not obvious. But if we open this class, we can have a look. So this is a class, sort of a DTO class. We have name, we have content, we have constructor. Technically, content depends on name, so it should not be different. We look at equals. Equals implemented the way to look at name and content. So everything is correct, except one tiny problem. We have equals, but we don't have hash code implemented here. And what happens if you implement equals but don't implement hash code? Hash code is default. There could be some random number depending on the where your object is located, so technically an address. And you violate the equals hash code contract. So how can we fix it? Let's generate equals hashcode. I don't think returning 0 is a good hashcode, so maybe let's like this. Do you think it's a good hashcode? Raise your hands if you think it's a good hashcode. So yes, this is not a good hashcode because you still violate the contract. And the contract is if two objects are equal, their hashcode should be the same. Otherwise, you face the problem that we faced, and that problem led to a memory leak. Let's get back to our presentation. So equals hashcode are sort of curves. We need to use them because our application is built up of these methods. But if we don't use them carefully, we might face some problems. So equals hashcode should be used properly. You should always override equals and hashcode together. And you should not violate the contract. If equals returns true, hashcode must be the same. And one more important thing to know, that hash map keys must be immutable. If they're mutable, you are not safe in terms of your hashcode might be recalculated, and you have the same problem with memory. So in Sonar, we have rules to deal with issues like this. So equals and hashcode should be written together. However, we don't have a rule that you're not violating the contract, because honestly, it's a little bit hard to do through static analysis. However, there is a tool. There is a tool that can help you to verify that equals and hashcode in Java do not violate the contract. So you can have a look at these links. And this is how it looks. It's just a one-liner, but you can test whether you violated the contract or no. So we found the root cause. Now it's time to fix something else, to investigate some other memory problems. And sometimes it's not that easy as just equals and hashcode. So let's have a look at a different example. When I look here, as I previously told you, there should be something catching my attention. But I look, and I don't almost see anything. We can try to look here, like look at byte array. Let's look at GC roots, here. And honestly, it doesn't say me much. So it doesn't reference any of classes that we wrote in our application, and I'm a little bit stuck. What we usually do when we are stuck in investigation and Visual VM, we can use another tool. And another possible tool is Eclipse Memory Analyzer. And this one is a little bit more advanced than Visual VM. And one of the most important things that I like to use is different reports like leak suspect. So technically, you just give this tool a heap dump, and you can ask for some leak suspect. And have a look there. I can cancel this request because I already done it before. So this is the leak suspect. And it shows me some similar report, like we have something that is referenced, and that's why it's not collected. And here we can see that the problem is somewhere in an array of objects, which are small objects, but if you look at the size that they occupy, they're not that small anymore. And what's the thing? When you look at the package and the class name, it's big object, $small object, something, add something. What does it mean? It means that small object is inside of a big object. So let's have a look in the code. So, yeah. This is small object. This is big object. It's big because we initialized it with 1 million of new strings, and it occupies a big amount of memory. And here we have class small object, and this is not static. And even IDE screams at you that please make this static. The point is that if your class is not static, it holds the reference to outer class. And while you created new big object dot new small object, you might think that big object disappears. However, it's not true, because every instance of small object is referenced by an instance of is referencing the instance of big object. And how we can fix it? We can use IntelliJ refactoring and make it static. And this way, small object doesn't reference big object, so we are safe. To get back to our presentation, we should be careful with inner classes. First of all, in most cases, they should be static. It's a very rare case when you need a non-static inner class. And if you still need it, you should keep in mind that it had a reference to the outer class. And we have a rule that helps you to identify the classes that should be static. And one of the last examples that I want to show you, it's a little bit easier than this one. We can see that still array of bytes occupies most of the memory, but we can also see that dominators by retained size are task threads, which is suspicious. And if we look here, we can look at some JC roots. Sorry, something not here. Okay, demo effects cannot find anything interesting. So yeah, the point is that there is something fishy with threads. What could be fishy with threads? Let's have a look in the code. And here we can find out that there is a thread local. What's the problem with thread locals? Usually, thread locals live as long as your thread is alive. So once your thread disappeared, your thread local disappeared. However, you are not usually creating threads with new. You are usually using some thread pools or executor services or anything that is reusing threads. And the point is that if you're reusing threads, your thread locals are still there. And if they occupy a huge amount of memory, they will be there until you clean it. So you can see that you set something in a thread local, but you never unset it. And this leads to a memory leak. So let's get back to our presentation and thread locals. Thread locals live as long as thread is alive. Thread locals should be unset manually. And in Sonar, we also have a rule to track issues like this. So, okay, we found out some small common mistakes with memory. Of course, there are not all the mistakes. There are a lot more. It's just that we are limited in time, and I cannot show you everything that could be wrong, but at least something and to give you some ideas. The next step, as long as getting back in shape, is to improve things. So you don't have huge problems, you don't have leak anymore, but let's do better. Let's go the extra mile. And here I would like to talk you a little bit more, with you a little bit more about memory leaks and memory footprint. According to OWASP, memory leak is a situation when you're using memory that you don't need. And memory footprint is a little bit different. It refers to the just total amount of memory that you're using. So fixing memory leaks, it's more like firefighting. You already have some huge problem, and you need to get rid of this. While reducing memory footprint, it's more about just some tiny changes. You're already in a good shape, but you want to be have more muscles, have less fat, whatever, and have some nice abs. This is about reducing memory footprint. So fixing memory leaks comes first, and then you can think about what you can improve. So what we can do to reduce memory footprint? We can remove references manually. For example, like we did in C++, set everything that you don't need to nulls. You can use custom class loaders. Because as I told you, if you're using default class loaders, your static members live forever. But with custom class loader, you define the life cycle of your statics. So if you want to get rid of some statics, you can use custom class loader, and this is one of the examples how you can do this. Another possible idea could be try to look at your code and minimize the living scope. For example, you're using something global, but you just need it in one tiny method, so prefer local things instead of global things. Prefer local variables instead of fields or static fields. And do all the necessary cleanup. If you still need something global, make sure that you clean after you don't need things. And another idea could be to use weak reference. I don't know if you ever heard about this, but in Java, there is a nice mechanism of sort of a telling garbage collector that if this object is referenced only weakly, and if you need some more memory, you can still collect it. And you just need to have some mechanism how you recreate the object. For example, like this, we create some object, garbage collector can collect it, and if it was collected, we need to recreate it again. But I need to warn you. When we are talking about reducing memory footprint, we need to find some balance. Sometimes, if you just want to do some cosmetic changes here and there and here and there, you can lose too much memory, which is great. However, your application can have a decreased performance because now you spend more time of loading classes again and creating static fields again and recreating some objects that were weakly referenced. And for example, the same happened to me when I lost too much weight. It was harder to me to lift heavy weights and even to lift my baby. So you need to have some balance. And you need to find what's more important in your exact case. So we know how to improve it. And the last step in the fixing and making your application fit is to prevent. Because we had some problem in the past. We fixed our memory leaks. We reduced memory footprint. We are now satisfied. But we need to make sure that the problem will never happen again, at least in the same place. So what we can do to prevent? Remember how it all started. You all probably forgot, because I was talking a lot about some other stuff, but it all started with Alexei Shepelov, who wanted to analyze Java and C++ code of OpenJDK in Sonar Cloud. And he failed. So I trained you a little bit on some smaller examples, but are you interested in real hardcore? Do you want to have a look at the real heap dump of our analyzers analyzing OpenJDK? So I'll show you. Here it is. Now it's not byte array anymore, but it's char array. And it took me a lot of weeks and months to understand where the root cause, but I'll just give you the right path because we don't have so much time here. So we have an array of chars. And they look a little bit strange. And if we click on a preview and show all, you can see that it's actually some file. So technically, this string, this char array, represents the whole file in source code of OpenJDK. Let's have a look and understand why it's referenced. So here are GC roots. You can see that it's referenced through abstract syntax tree, some meta trees. So maybe let's get here. Again, it's referenced through IST, through a compiler. So here and here. So it's everywhere, it's the same pattern. This string represents the source code, and this comes from some element in abstract syntax tree. So what happened? There was a regular expression check in our analyzer. So some rule that tells you that in this regular expression you have a problem. In order to be a little bit more optimized, this regular expression was caching some of the members of the IST. And in abstract syntax tree, there was always a reference to a root. And this root holded the string, which was like the whole source. And if you have 1 million files, you have 1 million of such strings in memory. And yeah, one of the biggest leaks were in this rule. And if we have a look at the source code, this is the field that sort of cached these ASTs. And if we look here at how it was used, it was created. We get something from there, we put something, but we never clean it. So for the whole analysis, it was just growing. And of course, it was an old version. And before I show you what's in the new version, I need to explain you a little bit more. So that was the leak in Sonar Java. OK, but it doesn't answer the question why the out-of-memory happened in C++. And this is another interesting thing that we found out. Plugins in our products are sort of kept in a list. And they're executed one by one. But because they're still referenced from the list, they live through the whole, analysis. It means that Java plugin did its job, left some garbage in memory, and then C++ plugin is starting its job, but Java plugin is still occupying some memory. And it happened that Java ate 90% of the memory. C++ was left just some tiny piece and threw out of memory. So it was not really fair to ask our colleagues from C++ team to fix it, because it was not their problem. It just happened that out of memory was thrown by their analyzer. What we could do in this situation? First of all, we could do some cleanup. You know that plugins can write some garbage in the memory. Let's just clean all the potential problems and put nulls everywhere we can see the state. Another idea is to reduce the life of plugin and, for example, use some queue. Because if we used queue and polled it, it means that Java Analyzer did its job, then it's destroyed, and then C++ Analyzer has all the memory. So no out of memory there. So in order to prevent in general case, we need firstly to follow a healthy diet that I'll show you a little bit later. Then you need to monitor usage of your memory, look at GC logs and understand what garbage collector is doing from time to time, perform some stress testing For example, analyzing OpenJDK, which is like one of the biggest Java projects, is sort of a stress for our analyzer, so we can find some paths that are not executed on other projects, so we can understand it better. Use tools like Visual Memory Analyzer, and some other tools, and add tests. How we can actually add tests about memory? You curious about this? So there is some tool, some project called Java Object Layout. This tool can actually show you how much memory is occupied by this or that object, or what is the layout. And it can even show you retained size of the object. Why we cannot just assert on this? So we remember that we had some problem in big object like some time ago. We fixed it. But how about adding a test that the amount of memory that is occupied by this object is less than some maximum count? So next time you introduce some problem on this object, you will see this test failed. And you can decide whether it was just intentional or whether you introduced some leak. And to finalize things, I think it's important to mention again all the problems that we faced. First of all, avoid statics and mutability. Clean thread locals, free resources, avoid non-static inner classes, but if you still need all of this or some of this, be careful and remember about the consequences. Reduce the scope of the references, prefer local instead of global, and monitor from time to time, because if you introduce some leak, try to fix it earlier, not when it's 1 year in production. And I, on purpose, haven't showed you what's in the master of that object, because I wanted to ask a question. If you're interested how the story ended, so maybe raise your hands if you think that the story ended successfully and memory leaks were fixed. Well, not a lot of people. You're like, don't trust my team, don't believe in me. And raise your hands if you think that we failed. What others think? I saw some people raising hands twice, so I don't know if you have some issues. But yeah, okay, I think that's enough holding the intrigue. Let's see the end. So it's ended with a couple of tweets of Alexei Shipilov, where he explained that he switched to a smaller VM, found out of memory, reported, got for confirmation that this was indeed a leak. And then we deployed the fixed version of Analyzer. And from not being able to use 3 GB of RAM, the analysis of OpenJDK went down to 1.2 at max, which is a great achievement. I expect some applause here. And Alexei received this nice T-shirt. So if you face some problem with our products, don't hesitate to contact our community forum or us or our developer advocates who are actually also at this conference. Because if your contribution was valuable, like this one, you can receive this T-shirt as well. And here are some useful links that I used while I was preparing this presentation. So you can take some photos of this. And useful tools like Visual VM. You see that it was able to show me at least 3 out of 5 leaks. Eclipse Memory Analyzer, which can help if Visual VM cannot. Also Eclipse equals verifier. Another nice tool is Java Flight Recorder. I think you've heard it today on a different presentation, so I'm not going to talk about this a lot. Java Object Layout, You can use it just to have a look at what's going on with your project, or you can even do some unit tests using this. And of course, Sonar. I could not mention this. And you can see that there are a lot of rules that can actually signal you about memory problems before you have them in production. And some kudos. Big kudos to Evgeny, who is, first of all, my husband and now taking care of my kids, so I can be here and talk to you. And kudos to him for helping me when I was analyzing these issues with memory and some ideas for this presentation. So without him, it wouldn't be that. I don't know if you like it or not, but it wouldn't be like this. And some kudos to huge kudos to my teammates from GVM Squad, who not only helped to investigate these issues, but actually fixed them. So I am able now to present you this successful result. And thank you for your attention, for surviving till the end. And do you have any questions?
Hello? Hey, I'm sorry, we ran out of time, so maybe they can reach you outside. We need to prepare it for the next talk.
Yeah. For questions, you can just ask me directly after the talk. Yeah.
Thank you very much.